A very good evening to one all present over here. Myself, Dr. Sheena. So today I'll be dealing with the subject dental materials, and on that, the subject session 1 physical properties and impression materials. So why physical properties? As dentists, we come across lot of dental materials directly or indirectly. So if we know the physical property or the mechanical property or the biological property, we can actually completely utilize the material to its maximum extent. So when coming to the NEET MDS examination, this is one of the most important topic, but it is really easy to understand too, because there are only certain terminologies and certain related concepts that you have to keep in mind so that you can easily answer the questions in your NEET MDS examination. So let us go into the subject. So what is stress? So before going into stress, first of all, you can see, I'll draw an image. This is one of the body. So when I apply a load from outside, L, what the body tends to do is it will slide. It will try to slide away. But at the same time, the material will develop an internal resistance. This internal resistance against the outside load is called as stress. So whenever you see an internal resistance, it is actually stress. So internal resistance of the body that is developed because of the load which we apply outside, it is called as stress. Stress, since it is happening in a particular area, it is actually given as force per unit area. So this is one of the questions that was asked for your MCQ. Stress is defined as, so it is of course the internal force that is opposing a applied load. From outside, there will be a load. There, when we apply a load within the body, it will actually produce a resistance against the load. So the answer is the internal force opposing an applied load. So based on the properties, it is being classified based on the direction of force. It is divided into three: tensile stress, compressive stress, and shear stress. So what is tensile stress? You can see the image. There are two sets of forces that are directed away, which is in a same straight line. That is called as tensile stress. What tensile stress does is like it elongates or it stretches your body. Now, compressive stress. Compressive stress means there are two forces. Again, they are moving towards each other in a same straight line, towards. So it compresses the body. Right, as the name suggests, it will compress the body. Now, what is shear stress? Shear stress is again two sets of forces that are directed parallel to each other, but not in a single straight line. See, one force might be like this, another force might be like this. So what happens is like there will be torsion or rotation taking place. And it often, this is twisting or torsional forces take place because of the shear stresses. And another thing is like it resists the sliding of one portion of the body over other. So the compressive stress causes the compression of the material. The tensile stress causes the elongation of the material. Shear stress causes the torsional or the slight twisting of the material. You can see the material getting twisted. So sometimes all these forces take place together. The compression force, tensile force, as well as the shear force comes together. They are called as the complex stress. Sometimes what is complex stress might be a question. So you need to answer it as the combination of all these stresses. So what is strain? So as I said earlier, when we apply a load outside, there is an internal resistance developed within the body. This internal resistance is called as stress. So what happens sometimes? So what happens is that it resists the load that is coming from outside. Sometimes the resistance is very less. The load is very much more. So there will be slight movement of the body. From this position, it might move to this position. Right, this is called a strain. Strain is actually the change in length when a stress is applied. Understood? In the early case, there was only a resistance developed. Here, there is change in, because the resistance built within that body is not able to resist the load from outside. So it might move a little bit, showing as strain. Strain is always the change in length or the deformation in the length by the original length, which does not have a unit, always shown in percentage value, right? So what is strain? Strain is defined as, of course, a deformation that is resulting. There will be change. There will be change in the material's position. That is a deformation or change in the body resulting because of the applied load. What is Poisson's ratio? This is very important. Whenever a body is subjected to a force, the force can be of two types, either a tensile force, which pull the body, or a compressive force, which push the body. Just see the image. This is one of the body which is having a diameter of D, and you can see this is the length L. So there is some force, tensile force applied. You can see the body's near position is this one, which have changed to delta L and a diameter of delta D. So, as I said, there is no change in the volume. If it is 100 is a volume, that is a volume after we pull also. There is just change in the dimension. In these cases, there is two strains that is developed. One is the longitudinal strain on either side, also called as the axial strain, and lateral strain on the either side. So the Poisson's ratio is lateral strain by longitudinal strain or axial strain. So just consider this is a ratio whenever a body undergoes certain like stresses like tensile or compressive stress, they move to a newer position, but the volume inside that change, it remains as such. So what happens is like Poisson's ratio is actually the strain that is developed on either side, that is longitudinal, that is the lateral, that is a lateral strain to that of the longitudinal strain on either side, also called as the axial strain. So there is something called as isotropic material. Isotropic material are those material where the volume is confined. Even there is change in the dimension. Think that the material is having a weight of 100 kilogram. Even after we pull or push the material, it will remain as such. The volume is 100 kg itself. That is isotropic material. The volume remains the same. For an isotropic material, it is having a Poisson's ratio of almost 0.5. So this is one of the questions again asked for your NEET MDS examination. Now, very important concept that you have to keep in mind, what is stress strain curve? So whenever a material we apply a force, it goes from one region to another. That is the elastic region to plastic region. Elastic, you know, when we pull a rubber band, when we leave it, it comes to its original position. This is actually the elastic region. What is plasticity? When we pull it again to a particular strength, it breaks. That is elastic, it moved to a plastic stage and it's fracture. Four important things that you have to keep in mind in the stress strain curve is proportional limit, yield strength, ultimate strength, and fracture. See the proportional limit. According to Hooke's law, we know that stress is directly proportional to the strain. Consider this body. When I apply a force like this is a stress which I developed. There is a change, deformation that took place. But when I leave the stress, it comes back to its normal position. This is the proportional limit. That is, stress is directly proportional to strain. When I applied a force, when I left the force, it came back to its normal position. That is the proportional limit. So what is yield strength? You can see yield strength actually comes under elastic region. That means, again, in yield strength, when a material is bent, it comes back to its normal position, but stress is not directly proportional to strain. When I apply a force of 5 Newton, it produces a change accordingly, that is of 5 Newton. But in yield strength, even though it comes back to its normal position, the stress is not directly proportional to strain. So that is the difference. What is the difference between proportional limit and yield strength? Proportional limit, it is according to the Hooke's law, where stress is directly proportional to strain. The material comes back to its normal position. But what is yield strength? The stress is not proportional to strain, but the material comes back to its normal position. Understood? Now, what is ultimate strength? This is the area where the material have moved from elastic to plastic. Means I have applied a force, it remains as such. It does not come to its normal position. It will remain as such. It is not coming to its position. This is called as what? Ultimate strength. Next, when we actually give more force, it gets fractured. So the ultimate strength is a strength till which fracture does not take place, but it cannot move to a elastic region also. I hope you understand. So there is two important concepts: elastic region, plastic region. Elastic means it can go back to its normal position. Plastic means it will rupture once it goes to a particular strength. So in elastic, two terms are there: proportional limit and yield strength. Proportional limit, strain directly proportional to stress. Yield strength, even it goes back to its normal position, stress is not directly proportional to strain. Ultimate strength means material does not come back to its normal position, but it doesn't fracture. When we give more of a force, it fractures. Understood? So what is proportional limit? Again, this is the area where stress is directly proportional to the strain. And see, when stress is increased, strain is also increased. Strain is double, stress is also double. It is directly proportional. So what is modulus of elasticity? Within this is actually the proportional limit, right? So here you need to think about two important terms: modulus of elasticity and resilience. So I hope you understood Young's modulus, elastic limit, yield strength, after that ultimate strength and fracture. Within this proportional limit, there is two important terms that you have to keep in your mind. First is modulus of elasticity. Second is resilience. What is modulus of elasticity? One is modulus of elasticity. Another name might be elastic modulus, Young's modulus. All you have to memorize is like modulus is there. So you need to think it comes under the proportional limit. So it is actually you can remember by this quote, same. This is modulus of elasticity. S means stiffness. Whenever a question comes on modulus of elasticity, you need to memorize this mnemonics, same. Modulus of elasticity actually represents the stiffness of the material. This is a very important question for your NEET MDS. And the modulus of elasticity is equal to stress by strain because it comes under the proportional limit. So the stress is directly proportional to that of the strain. So just think, there is a very hard material or stiff material. Means what? We need to give lot of pressure onto that material, but the material does not move. So stress is more, strain is less. Stress is more, but is there any movement taking place in the hard subject? No. So strain is less. So Young's modulus is more. That means stiffer the material, higher will be the modulus of elasticity. Stiffer or harder the material means when we apply the force, there will be no strain taking place. So there will be no movement. Young's modulus will be more. So Young's modulus comes under proportional limit. Stress is directly proportional to strain. Stiffer the material, more will be the Young's modulus. Flexible material, less will be the Young's modulus. Very important topic and very important thing that you need to memorize. Same stiffness, like modulus of elasticity shows the stiffness of the material. Again, stiffer the material, higher the modulus of elasticity. So this is one of the question again asked. The stiffness of a dental gold alloy is determined by its, see, there is stiffness. So we need to remember SAM is same. So it is based on the modulus of elasticity. What is resilience? As the name suggests, resilience means this is actually the energy. It is actually, resilience means energy. You can memorize like RE. This is energy. Resilience is basically the energy that is absorbed by a material when it is stressed not more than proportional limit. That is why I said modulus of elasticity, resilience, Young's modulus, everything comes just below the proportional limit where the stress is directly proportional to strain. Resilience, you need to actually memorize. It is the amount of energy the body absorbs when we apply a force within the proportional limit, right? So another important thing is S. It actually is associated, as I said, modulus of elasticity is actually associated with actually the code SAME. Similarly, here it is associated with springiness. Whenever springiness, there is a question, you need to think that it is resilience or energy. When you think that, you can actually, the two terms are there in the name itself, resilience. E for the energy that is absorbed by the body. S is actually the springiness. So next question, the greatest stress which can be produced in a material such that the stress is directly proportional. So directly proportional means we have one thing only. Either it is like proportional limit. So proportional limit is actually the answer. Next is elastic limit. You know, again, this is the point called as elastic limit. It is within the elastic range. Means when we actually apply a force, it comes back to its normal position without any permanent deformation. But the stress is not directly proportional to strain. Sometimes elastic limit is always or also being told as the yield point. Both having the same terminologies in most of the cases. So elastic limit means proportion. It comes back to its normal position, but it is not proportional. Stress is not directly proportional to strain. So this is the difference, right? Next is what is toughness? Toughness, as the name suggests, TO, it is a total area under a stress strain graph. There is total area, that is the elastic area and the plastic area. So the total toughness means what? A material is tough means it is hard to break. Means even we apply a force in the elastic phase, even we apply a force in the plastic phase, it have to pass all that phase to get fractured. That is called as toughness. That is the energy required to fracture, or remember as TO, the total area under a stress strain graph. Sometimes the question might be A, B, which represent the total area in a stress strain graph of toughness. So you need to answer it as A plus B, that is the complete elastic as well as plastic area. Now, what is brittleness? Just the opposite of actually toughness. As I said, sometimes some of the material, when we apply a force, if it is proportional, within proportional limit, if we apply a force like this, it comes back to its normal position. When the material is brittle, within the proportional limit also, when we apply a force, it fractures. That is called as brittleness. Okay. Another important question. A material behave in certain way above and below the proportional limit on a stress strain curve. Which of the following is correct? See, the question is, if this is the graph and this is the proportional limit, what is above this and what is below this? We know below this, it is what? Elastic. And above this, it is plastic. So see, above the proportional limit, the material function is plastic. Of course, plastic. And after that, it fractures. And below that, it actually acts as elastic material. Right, that is the answer. What is ductility? Ductility is the ability of a material to withstand permanent deformation under a tensile load. That is whenever we actually apply a force so that the material moves to a wire form. That is called as ductility, where a ductility is a tensile stress is given. Malleability means ability of a material to avoid the permanent deformation in a compressive load. This is very important that you have to keep in mind. Ductility is tensile, malleability is compressive force. So the question sometimes asks us, which is the most malleable and ductile material? It is gold, which is ranked first, followed by silver, which is second. On ductility case, platinum is actually the thing that is ranked third. In malleability, it is copper. So these are some of the questions again asked for your NEET MDS examination. So that was the main things: stress, strain, combination, complex stresses, stress strain graph, proportional limit, after that yield strength, after that ultimate strength, after that fracture. Within proportional limit, you need to think about resilience and modulus of elasticity. Resilience, within that name is a RES. E is for the energy absorbed, S is for the springiness. Just keep in mind all those terms. It will be very easy for your exam. Next is hardness. So how we say a material is hard? When we actually push or when we actually give a boom to the material, there if it doesn't cause any scars or any fracture or to the area, it is called as actually hardness. Similar in a case, if a material is said to be hard, there are certain testers like these instruments where a load is applied on a material. This is a sample thing. This is actually one of the samples whose hardness has to be tested. We'll apply a load on its surface. It is the ability to resist scratching or abrasion. When we apply a force on a particular material, there should be no scratch or no abrasion. On those cases, we can say that the material is hard. This is very important term. The material that resists the scratch or abrasion is called as hardness. What are the type of hardness? First of all, there are 4 types of hardness. Grinnell test, type how we actually calculate the hardness. Grinnell test, Rockwell test, Vickers test, and Knoop test. These both are called as macro hardness test. Very important. Vickers test and Knoop test are called as micro hardness test. Okay, you understood? Both BR are macro. Vickers and Knoop are actually micro. So what is the difference? Only important points has been noted. First of all, Grinnell test. Grinnell test, we know it is BR. B is for like macro hardness test. First important thing. You can see in this tester, there is a small ball here. This ball we are applying on the material and trying to put indentation. So how we calculate the hardness? The load which we apply by the load, this is the load. There will be some 500 Newton force will be actually applied. That is the load to that of the area of indentation. This is the material. This is the subject onto which we apply a force. See, there will be indentation like this. The area is calculated and applied here. That is how we get a hardness. Very nice, very easily explained. Grinnell test, round. You can see there is a small steel ball of diameter 1.6, very important. It's steel ball of 1.6, which we'll apply on the surface of a subject. So how we calculate hardness? The load which we apply to that of the area of indentation. Another important thing, Grinnell test is only used for metallic and metal-based materials in dentistry. Brittle materials are not used. That is why we called it as a macro hardness test, where we'll be applying only for the metal and metallic instruments or appliances in dentistry. Next is Rockwell test. As I said in the earlier case, there was small round ball that was used. Here we use a conical. You just think from rocks we get diamond, right? Just think like that. So here we use a conical diamond points. It is like a conical diamond points that is actually applied on the surface where the hardness need to be actually checked. And there will be indentation like this, right? The depth of penetration is calculated here. The early case, there was a formula, but here we'll be actually calculating the depth of penetration, right? Another important thing, again, this is not used for brittle material. It is used for what? Metal and metallic substances, as in the case of early stage testing. So this is called as macro hardness test. Very important. Next is Vickers test. Vickers test is like micro hardness test. And in the early case, it was conical diamond shape. Here it is square shape. You can see it is almost a square shape, right? Another important thing is it is similar to actually the first Grinnell stage, where we'll be actually calculating the load to that of the area of indentation. First, as that of the first formulation, Grinnell formula. Second one, just the depth will be calculating. Very important thing that you need to, in the first 2 cases, we actually used it for metal and metallic substances. Here we'll be used for actually casting gold. Here the hardness is actually calculated with the help of Vickers test. Next is Knoop test. Knoop test, as the name suggests, no. It doesn't say no to anything. It actually helps in the calculation of a thin plastic, metal, brittle material, everything it calculates. The hardness of every material is calculated by Knoop test. Okay. And the size of this thing is almost a pyramid, diamond shape. So all the shape of the tester, it is very important to keep in mind. The first one was like ball, second one was like conical diamond shape, third one was like a square shape. Here it comes like a pyramid, diamond shape. So this is very important. First two are macro hardness, the other two are micro hardness. First two we do not use for brittle material. Last two we use for brittle material. Especially noob hardness is used for the entire brittle material. Very important, another question, Shore and barcode test. So this is again a tester machine which uses for measuring the hardness of plastics and rubbers. It's very important only for plastics and rubbers. That is the flexible material. So mainly for plastic and rubber, it is Shore and barcode test. Another important question, the hardness number which does not depend upon the ductility of a metal means what? As I said, ductility of the metal means there will be elongation taking place, means tensile force taking place, right? Brittle materials, we cannot apply a tensile force. So which is the test where brittle materials is used? That is actually the Knoop's hardness test. So of course, the answer is actually hardness number which do not depend upon the ductility, where we are not using the ductility of the metal, because in brittle material, we cannot actually check the ductility, whether it is just stretching or not. So in those cases, the answer is actually Knoop hardness test, because it can be used for all the materials like brittle material where ductility is not a factor. Next important, ability of orthodontic wire to spring back to its original springiness, which was the answer. It is, of course, we need to think resilience. Resilience, RES. E for the energy, S for the springiness. So the answer is resilience. This is how you actually correlate the codes on mnemonics which we use to that of the answer. Next is, what is ultimate tensile strength referred to? What is it? We have four important points: proportional limit, yield strength, ultimate tensile strength, last fracture. This is the area which is just before the rupture. So this is the answer. A is the answer. The stress before the rupture. So simply keep that graph in your mind. Just the codes go to the answer. Right. This was all about the hardness test and also based on all the important things in stress strain graph. Next is, what is wetting? Very important subject, very important topic. Again, you like asked for the MCQ questions in NEET. What is wetting? Wetting means what? Simple language, the liquid which can spread on a particular surface. That is called as wetting. What is contact angle? The angle that is formed by the liquid surface to that of the interface is actually called as the contact angle. Very important thing that you have to keep in mind is wetting is indirectly proportional to the contact angle. Very important. So think the contact angle is 0. Means what? The contact angle is actually 0 means what? Wetting is actually means alpha is equal to actually 0. It means that there will be actually complete spreading of the material taking place. It is inversely proportional. As we go actually to a larger amount, like more than 180, there is no wetting. Angle is more, wetting is less. That is why I called it as inversely proportional. See, the contact angle is 0. 0 means it is nil. It is very less. So the wetting will be more, inversely proportional. Think it is 180 degree. The contact angle is very high when compared to 0, 180 degree. So the wetting is very less. That is why I told wetting is inversely proportional to that of contact angle. Keep in mind. 0 means there will be complete wetting of the substance. When it goes very high to 180 degree, the wetting become decreased. No wetting take place. So it is again a very important chart that is you need to keep in mind. 0 means complete wetting take place. 180 means just the opposite. Higher the value, less the wetting. No wetting take place. 90, incomplete wetting. At 90 degree, there is incomplete wetting take place. At less than 90, good wetting taking place. So if lower the wetting, more will be the contact angle. Right. How much should be the degree of contact angle for proper wetting? So proper wetting means complete wetting to take place, more the wetting, less the contact angle. So it should be the lowest value in this is 0. So 0 is the wetting is inversely proportional to that of the contact angle. This is very important thing that you have to keep in mind. Next important question. The ability of an alloy to withstand mechanical stresses without permanent deformation. Again, the question is without permanent deformation. So something is reflected by its. What is the answer? It is elastic limit. Both proportional limit and elastic limit comes within the elastic area, right? So the only answer which is given is elastic limit. Resilience is the energy. It is not the stress that is developed. So you need to actually work on that. Resilience is the energy, but elastic limit is actually stress that is developed within the proportion, within the elastic range. Stress is not directly proportional to strain, but it comes back to its normal position, right? Next, very important topic again, linear coefficient of thermal expansion. Every material, when it exposed to a temperature change, there will be swelling or it comes to a shrinkage form. So that is called as the linear coefficient of thermal expansion. When there is increase in 1 degree Celsius, how much the material expand. This is a very important concept that we have to consider, because whenever we select a restorative material to a tooth, see, this is actually the tooth. So whenever we select a material to place inside this, we have to think or select a material whose coefficient of thermal expansion is similar to that of enamel and dentine. Why? See, the enamel coefficient is 11.4. Amalgam is 25. So what happens? When we increase the temperature, so whenever the oral cavity is exposed to a temperature change, the tooth will expand a bit. But the material like amalgam, if we place inside that, it is having a coefficient of thermal expansion about 25. So it will expand more. So what happens is like it expand more and it create more of a force on the tooth fracture. Or certain materials are having the modulus of elastic, the thermal expansion less. So there will be spaces created which causes secondary cadus, fracture to the tooth, etc. are the after effects which is seen if we mismatch the linear coefficient of thermal expansion, right? So the question sometimes asked is, which is a material which is having a coefficient of thermal expansion similar or near to that of our tooth structure? So you need to know what is the CTE of enamel. It is 11.4. Just keep in mind, it is 11.4. For dentine, it is 8.3. Very important, keep in mind. 11.4, 8.3. See, the material which have CTE very close to our tooth is first is the type 2 GIC. After that, it comes as the silicate. Okay, this is very important question. Type 2 GIC and silicate material. You need to keep in mind. So the question is, coefficient of thermal expansion of which of the following is most similar to that of the teeth? So we know that teeth means enamel or dentine, which is near to 8 and 11. So in this, GIC is not there. So the answer will be silicate cement. If GIC was there, you need to actually write the answer type 2 GIC followed by silicate, right? Next, very important thing is creep. Everybody know it is time dependent deformation that is taking place. What is it? Think about a material. This is a material. When we apply, just think 60 degrees Celsius, like heat is applied, it moves to a liquid form or it is flexible form. So we are making it into a position where we are applying only 58 degrees Celsius for like 15 minutes or like 15 seconds. So there will be certain changes that happen place in this material. It will be deforming, but it does not move to a liquid state. This is called as what? Creep. Creep is like a time-dependent plastic strain is called as a creep. Means a material is subjected to a particular force at a particular time and there is certain deformation taking place in that material. It is called as creep, right? So the force applied might be of two types, static creep and dynamic creep. If we are applying a constant force, continuously a force is applying, it is a static creep. If we are actually giving a fatigue type of test force or changeable or fluctuating forces, it is actually called as a dynamic creep. So keep in mind, creep is a time dependent plastic deformation. One, static is like, as the name suggests, a constant flow. Dynamic means there is a fatigue type of force. Question again. Which of the following property of dental material is time dependent? As you know, the time dependency is given, so just don't think much, give the answer quickly. Next, certain terms and certain questions that has been asked. I'm explaining that. What is latent heat of vaporization? The name itself suggests it is something is evaporating or something. So it is also called as latent heat of evaporation. Evaporation means what? It is the heat required to convert a liquid to gas is called as latent heat of vapor. The name itself suggests. So the liquid is getting converted into vapor. So the amount of heat that is required to change the boiling water to vapor. Since we have the vapor at last, it is the latent heat of vaporization. Next is latent heat of fusion. So what is latent heat of fusion? It is the amount of energy. Means something is fusing. Just think like that. When something is fusing, there will be release of energy. Here there is release of energy. Fusion, just keep in mind, something is fusing. So there will be release of energy. So there will be the amount of energy released when a liquid freezes. This is called as the latent heat of fusion. So FF, you just remember it as freeze. So this is actually the amount of heat that is released when a liquid get converted into a liquid freezes, right? Or liquid get converted into ice or solid form. What is sublimation? It is a direct change of a ice or a solid to vapor. There is no liquid form directly. Sorry, it get actually converted into vapor form. So these are the most commonly asked questions in the physical properties of the dental materials. First of all, the normal things which you use, stress strain graph. The second is actually the all the terms like latent heat of vaporization, etc. Creep value, toughness, resilience, etc. Just keep in mind, just keep the concept, only direct questions will be actually asked on that. Okay. Moving into the second portion, dental materials. On dental materials, it is impression materials. So we are very much used to the normally used dental materials. I am not going into the dental materials in depth, but I'll be actually explaining very important or repetitive questions that has been asked in the impression chapter. So there are certain terms that you have to keep in mind. First of all, just memorize this image. What is a solution? Solution is actually a homogeneous mixture, right? Nothing is there. I'm so sorry. Nothing is there. It is a homogeneous mixture whose particle size is very much less than 1 nanometer. Understood? What is a suspension? It is heterogeneous. There are a lot of things like a solution with a solid substance being suspended whose size is more than 1000 nm. It is called suspension. When something comes in between this, that is in between 1 nanometer and 1000 nanometer, it is called as a colloid, right? So always think solution homogeneous, suspension heterogeneous. In between this of a size range of 1 to 1000 nanometer, it is colloidal structure. So next is next very important. So hope you understood what is solution, what is suspension, what is emulsion. We have heard about paints and all. Liquid in liquid is called as emulsion. Just think about that term when we actually used to deal with paint. Emulsion is liquid in liquid. What is colloid? As I said, in between suspension and solution, it is and the important term is it's the fourth state of matter. Is called as colloid. Always another important thing that you have to remember is colloid have a sole gel form. Sometimes the solution, when there is a change in the temperature, it might get converted in the gel form. The gel, when we actually change the temperature, might actually move into the sole form. That is a solution form. So this is the 2 or 3 important points that you have to memorize when we talk about colloids. What is a hydrocolloid? When there is water in a colloid, along with the colloid, it is called as a hydrocolloid, right? Hydrocolloid are those colloids where there is actually a dispersion, water as a dispersion phase is called as hydrocolloid, and it normally have 2 important forms, sole forms and gel forms, right? So these are the important terms: solution, suspension, emulsion, hydrocolloids, colloids. Hydrocolloids have 2 types, solution and gel form. So another important question, the fourth state of matter is, now you know, it is colloid. Sol gel transformation is seen. We have talked about colloids. Colloid plus water is hydrocolloid. Hydrocolloid is a thing that have a sol gel transformation when there is change in the temperature, right? So very important thing, very commonly asked is actually the impression materials and its classifications. First of all, mode of setting. We have been using like agar arsenate in our clinical practice. Like based on the mode of setting, there are two types of setting taking place: chemical reactions and temperature changes. See the first one. There is certain chemical reaction taking place, so it is irreversible. That is called as thermoset. That is because of the temperature, because of the chemical reaction take place, there is change in the temperature, there is complete setting of the material take place. So this is three important terms. First is irreversible. It cannot come back to its normal position because it is because of the chemical reaction taking place. Next is thermoset. So what about the second classification? Temperature change. Temperature change is like instead of irreversible, there is temperature change. So when we actually change the temperature, it can come back to its normal position like our agar and all, our wax and all. So that is reversible and thermoplastic. So this you just keep in mind, chemical reaction and temperature change. Next is again rigid, and in that rigid and elastic is there. And just see irreversible, which cannot come back to its normal position, and it's also rigid. You can ripe fruits are liked by apes, right? So I used to actually memorize like that. Ripe, R-I-P-E, apes on the other side. R is like the rigid material. P is for the plaster. E is for the eugenol. Memorize. What is the elastic? Elastic means even though it sets, but it is having elastic property. A is all the alginate hydrocolloids. Second is actually all the polysulfides, polyester, means elastomeric materials, and is the silicons. Understood? Just memorize this box as such: chemical, temperature, rigid, elastic, ripe, and apes. R for rigid, and PE for the plaster and eugenol. The other is A for alginate, P for all the polysulfide, polyesters, etc. S for silicons, right? And next, actually, set by temperature change, which is rigid. We know our impression compounds and waxes are rigid, which is elastic. Agar is elastic, right? Try to memorize this. What are alginate? So what is the answer? What are alginate? Alginate are normally hydrocolloids. Hydrocolloids means it have a sol form as well as actually a gel form, right? Inelastic impression material. So which is the inelastic impression material? Which is the inelastic? Here it is the impression compounds is actually the inelastic, which cannot be actually come back to its normal position. It is actually it can come back to its normal position, but it is actually rigid type. That is the impression compound. Just memorize that box. It will make easy for answering all these questions. Which of the following impression material is rigid? So what comes in that rigid? It's like eugenol, right? So it comes zinc oxide, eugenol. So that was the classification on based on the setting, reaction, temperature, chemical, etc. Just memorize that is very important box. Impression technique are of two types: mucostatic and mucocompressive, and another is the selective pressure. But the question mainly asked is from mucostatic and mucocompressive. Mucocompressive means it claims to record the tissue in their functional and supporting form. That is, when the occlusal functions are taking place, it will actually compress and it will actually replicate all the structures. That is called as mucocompressive. An example for that is impression compounds for edentulous art, waxes and soft liners. Just think which we actually use for our edentulous teeth. That is because we'll be doing the functions like the functional movements. So we use the impression compounds as well as the wax. Just memorize that like that. What is mucostatic? Means the static. The mucosa or the structure or any functions is not disturbed. It is not acting as such, which we use the alginate impression, zinc oxide impression, plaster, all these comes under mucostatic. So very important, mucostatic and mucocompressive. Mucocompressive compression taking place for our edentulous arch, right? Next important, so you can remember as ape, again ape. The most mucostatic impression material. Which is the most mucostatic impression material? Mucostatic means what? It is not moving. So what is it? It is again plaster of Paris. Plaster of Paris, we does not give any like actions into that. Next is the most mucostatic among the following. What is mucostatic means what? It is again not moving. It is actually the zinc oxide paste. Zinc oxide paste, again the plaster of Paris, etc. comes under this. Next is impression compound. Some of the main important thing that you have to consider in impression compounds is, first of all, the ADA specification number is 3. Hope you have seen this in your ProSo lab, so it is much easy for your memorization. It is of two types, impression compounds and tray compounds. So impression compounds, we know that which is used for actually doing the impression. Tray compounds are for the tray extensions. We use the impression compounds. Very important, again, you need to memorize the composition because a lot of questions have been actually asked from the composition. Rose come to school by colorful car. You can memorize like this. Rose come to school by colorful car. So what is rose? Rose is actually rosin. Rosin is about 30 parts. Come is CO, copal resin, which is also 30 parts of that. And next is actually the school, which actually consists of the shellac, stearic acid, which is actually used as a plasticizer. And colorful means the coloring agent which we actually use. Car is mainly the carnauba wax. Hope you understand. Rose come to school by colorful car. Rose is like rosin. CO is like copal resin. School is which is by shellac and also stearic acid. Colorful is like the coloring agents which we add, and CA is carnauba wax. That is one thing that you need to memorize. Another important thing is actually, since the composition consists of waxes and resins, what happens is like strength is very less. You can see it is of lower strength. So we need to add certain fillers. So normally it consists of wax inside this. It is very less strength. Since wax, we know it is not having that strength. So what we need to do is like we need to apply certain filler particles into the material. So the filler particles which we commonly use is talc. Very important, which we commonly use is actually the talc diatomaceous earth, which is actually used for increasing the strength of the material, right? Another important thing is actually for increasing its plasticity, shellac and stearic acid is also used. And very important, another thing is gutta-parsha and bee wax. This helps in the plasticity. Just think about the plasticity property, which is attained by adding gutta-parsha as well as bee wax. Just memorize this mnemonics and just correlate, right? Because of wax, we need to add filler particles. Filler particles is like talc. So there is two important terms again. It comes to actually this. First of all is glass transition temperature. So what happens is like when we apply, just think like that, when we apply a temperature to a material, if it loses its hardness or on heating, it becomes a solid substance. That temperature is called as glass transition temperature. The temperature at which, this is a particular temperature, it might be like 36 degrees Celsius. This is the temperature at which this material loses its hardness to become like a flexible thing. And when we heat this material at the same temperature, it actually moves to a harder material. This is called as glass transition temperature, and we used to see in this material, right? Next is fusion temperature. Is a temperature at which the material softens to a plastic mass. That this is the fusion temperature, means we will be heating the material so that we can actually use this, which is more of flowable or more of a plastic material that helps in its use. That is called as the fusion temperature. So glass transition temperature is 39 degrees Celsius. You need to memorize this. Fusion temperature is 43.5 degrees Celsius. Another important property that you have to, it does not have much of a thermal conductivity. That is why we need to actually put in water for a longer period of time, because the material gets heated on the outer surface first and then it comes to its core surface. So we need to actually apply for a longer time or put in water for a longer time in order for its manipulation. So it become more of a flexible. And second is like high coefficient of thermal expansion is there. Again, less dimensional stability due to the wrappage is there. That is another important property. And the disadvantage is, of course, it is not mucocompressive. Mucocompressive means it will take all the functions of our mouth. It is not taking place. Next, very important thing is zinc oxide eugenol impression paste. So zinc oxide eugenol impression paste is normally actually used for, again, edentulous mouth, and it is of two types, hard and also soft is there. And it consists of actually two pastes there. The base paste, which is actually white in color, the catalyst paste, which is actually red in color. So the base paste, as the name suggests, it consists of zinc oxide, and the liquid mainly, the accelerator paste mainly consists of actually eugenol. And something you need to actually memorize again. Lanolin inside the accelerator helps in actually the flow. Lanolin helps in actually the flow. Very important. Second, the resinous substances. Any resinous substances help in actually increasing the flow. Just memorize the name and just try to correlate. Lanolin is helping in actually flow. Again, the resin also help in actually increasing the flow. Filler particles in the last slide also we studied, it helps in increasing the strength and also speed up the reaction. And again, CaCl2 is actually the accelerator, because calcium acts as actually a nucleus which helps in actually the faster acceleration of the process. So normal reaction, we know what happens is like the zinc oxide, it gets reacted with the eugenol to form eugenolate. So very important, water is needed for this reaction. Again, water is also a byproduct. This might be asked for in question where water has been used for a reaction as well as it is used as a byproduct. It comes out as a byproduct, that is zinc oxide eugenol. And zinc acetate have high temperature. The three important things that may accelerate the setting reaction is the addition of zinc acetate, high temperature, humid environment. These are the three important things that may actually accelerate the setting reaction. That is a very important thing. Another important thing is like how we can actually reduce the setting time. As I said, we can increase the setting time by using a zinc acetate, or a humid environment or a high temperature can actually accelerate. It will set fast. How we can reduce the setting reaction of zinc oxide eugenol? Just cool. What we need to do is like just cool the glass slab. That is one. Second is like add small amount of glycerin. Two. That is another two important things how we can actually change or how we can delay the setting reaction of zinc oxide eugenol. So these are the common questions that has been used, which is the two important things that helps in the accelerating the setting reaction. So those parts, one is the composition part. Second is actually what are the materials, how it accelerates, how it decreases the reaction. These all you need to keep in mind, right? See the question. All of the following can be used to slow down the setting reaction of zinc oxide eugenol paste, except. So what was the question that was asked? Like how it will slow down the setting reaction. First is like, as I said earlier, we can actually cool the glass slab, one. Second is adding the glycerin, two. Three is like altering the amount of toothpaste used and adding a small amount of water. We have never explained that adding a small amount of water can actually slow down the setting reaction. This is right. This is right. This is right. So adding the amount of water is not the answer. So that is why I said accelerating things and those which slow down the setting reaction need to be memorized. Next is, there are, as I said, there are two types of zinc oxide impression paste, type 1 and type 2. How we classify this two? This is based on actually the hardness they attain after the setting, because the type 1 zinc oxide paste is called as hard paste. The type 2 is called as soft paste. The first one hard paste because it sets within 10 minutes. The second one is called as soft because it sets in 15 minutes. So these are the important things that you need to memorize in zinc oxide eugenol, right? Okay, again, setting reaction of zinc oxide eugenol is best controlled by. This is both this answer are right for this question, but which is the question is like best controlled by. Best controlled by, it is always cooling of the glass slab. That is the most important thing, right? The advantage of zinc oxide eugenol impression paste is, of course, its dimensional stability. That is a very important property that you have to keep in mind. But again, I have explained this topic. What is lanolin is added? What reason? Again, to increase the flow. I have already explained lanolin is actually added to increase the flow of zinc oxide used on paste. So next, the best material for duplicating the cast is, of course, it is agar. Though before I'm going to explain agar, I just added a question. This material for duplicating a cast, it is always agar. I'll be explaining why. The best constituent of a reversible hydrocolloid impression is basic constituent reversible. Just think the term reversible. It can come back to its normal position. It is agar, right? So talking about agar, that was two answer we already got. It is reversible. It is an hydrocolloid. So see, agar is a hydrocolloid. We know that it has been actually collected from the seaweed. When it's set, it is having a brush heap appearance. Very important. Again, asked for actually Viva question. So what happens is like, normally it is called as a hydrocolloid because it can change from a solid to gel form, a gel to a solid form. Very important. That is why it is called as a hydrocolloid or reversible hydrocolloid. Alginate is a irreversible hydrocolloid. Actually, it can move from solid to gel, but it cannot come back. So it is called as, agar is a reversible hydrocolloid. Alginate is a irreversible hydrocolloid. And what happens, agar is normally in a gel form. We get it is like a jelly form we get. It is actually more viscous, right? So more viscous means what? Will we be able to take an impression? No. So we have to make this more viscous form to a less viscous form. So what we do is like we heat it at a temperature of 60 to 70 degree. That is, gel moves to a solution form. That is called as liquefaction temperature. I hope you understand. Agar is in the form of a gel. So we cannot use a gel for taking an impression. The gel has to be converted into a liquid form. For that, we will be heating it at 60 to 70 degrees Celsius and it become less viscous form, right? It become less viscous form so that we can take the impression. That is the liquefaction temperature. So you might be thinking, if we reduce the temperature again, just like 60 to 70 degree behind, it moves to a gel state. No. There is something called as hysteresis. That is, we might think that it took 60 to 70 degrees Celsius for becoming a gel to become a liquid. So if we come back 60 to 70 degrees Celsius lower, it might come to gel. No, before reaching 60 to 70, that at 30 to 40 degrees Celsius itself, it gets converted into gel form. So there is a time lapse or a temperature lag between the liquefaction and gelation process. This is called as hysteresis. Hope you understood. We'll be getting it in a gel form. This gel is converted into liquid form at 60 to 70 degrees Celsius. So we will be like thinking that it might actually get converted into gel form at the same temperature. No. In between there is a temperature that is 30 to 40 and more specifically 37 degrees Celsius. It gets converted into gel form. So there is a temperature lapse that is found. It is called as hysteresis. This is a very important term and this is very important like numbers that you need to keep in actually your mind. Liquefaction temperature is 60 to 70 degree and the gelation time or the hysteresis is at a temperature of 37 degrees Celsius. So coming to the composition, again very important, agar will be there, borate will be there. Borate, as the name suggests, like boxing, just memorize like borate, it helps in increasing the strength. So agar is a basic constituent, borate help in increasing the strength too. What happens with agar and borate is like when we actually apply plaster on the surface of that for taking an like a replica, it actually prevents the setting of gypsum. So to prevent that, what we add is like we actually add a sodium sulfate to retard the action of borate. Borate is having a function like giving strength, but they actually inhibit what? The setting reaction of gypsum. For that, we actually add what? Potassium sulfate. So these are the things that you have to keep in mind. Agar, borate, potassium sulfate. Again, wax is added as a filler material. So these are the four important things that you have to memorize in the composition of agar. Another important property of agar is synergesis and imbibition. What is synergesis? Synergesis is actually the loss of water from the surface of an impression is called as synergesis. Imbibition means they have an property to absorb water. So these two important properties are actually seen in agar. Right. Again, the reproduction of the details is like 25 micrometer. This is one of the question again asked for agar. Working time is 7 to 50. Setting time is 5 minutes. Which material undergo hysteresis? Now we know it is the reversible hydrocolloid, that is agar. Right. Brush heap structure is found in. As I said, that structure is actually found in agar. K2SO4, that is potassium sulfate, in agar is 4. What is the answer? As I said, setting reaction or strength has been increased by the borax. But the borax inhibit the setting of gypsum. So to accelerate the setting of gypsum, we actually add K2SO4. Now, what is the dilation temperature for agar? 60 to 70 degree, they form liquid. Again, to form liquid, it need not go complete 60 to 70 degree. That is the 37. That is about 30 to 40. That is 37 to 50 degrees Celsius. Centigrade is actually the answer. So this is another question. The technique, we'll be combining the technique of reversible and irreversible hydrocolloids for taking impression. So this is because we'll be using agar as well as alginate at the same time, right? That is actually called as laminate technique. As the name suggests, just think that laminate means we'll be actually using both the reversible and irreversible material, right? So which of the following increase the strength and reduce the viscosity? You know, strength, which increases strength of agar, of course, it is actually the borax. So coming to alginate, alginate is again a hydrocolloid, but it is the difference from agar is like it is irreversible hydrocolloid, right? It is actually one of the irreversible hydrocolloid. So what is the composition of actually alginate? Alginate is also taken from one of a seaweed in the form of alginic acid. The problem with alginic acid was that it was non-soluble. It was non-soluble. So for like taking impression, it should be soluble. So what they did is like they bombarded or they added this alginic acid to sodium and potassium to form a salt. Simple. Alginic acid, since it is insoluble, sodium and potassium was actually added to form salt. What salt? Sodium and potassium alginate. So this was the salt that was formed, right? And what happens is like, and to that, what we added is that calcium sulfate was there. Why calcium sulfate is there? This is a form which actually provides calcium. So since it has to get converted from a sol to gel, to get converted to a gel form, we need to provide calcium. So calcium is given by calcium sulfate. So what happens is like sodium potassium alginate react with calcium sulfate to form calcium alginate gel. Right. So this is a very important thing that you have to keep in mind. Alginic acid converted into salt form by sodium and potassium, and the salt form is to this calcium phosphate is added to accelerate the reaction. The last product which is formed is calcium alginate gel. So again, the gelation time of alginate is controlled by adding of retarders, that is especially the usage of cold water by the operator. This is very important. How to retard? It is by the addition of cold water. Next question. Impression material which have a high incidence of air porosity. This is another important thing that you have to keep in mind. Air porosity is mainly seen in alginate impression material. Okay, all those were about hydrocolloids. Hydrocolloids, as I said, it is a combination of water and a colloidal product. And these comes the elastomeric materials. Elastomeric materials is the rubber-based materials, right? The first is polysulfide. I have just added the other names and the important properties that you have to keep in mind. Polysulfide is the first dental elastomer that was actually introduced. It is also called as vulcanizing impression material because it consists of rubber. It is mainly from rubber, so it is called as vulcanizing. Mercaptan is actually a composition which is actually present in the impression material, so it is also called as mercaptan impression material, polysulfide. Another important thing about composition is the lead dioxide which is actually present that is responsible for the brown color to that of the impression material. It is actually a disadvantage with polysulfide, right? Another important thing is the byproduct that is formed is actually water. That is a byproduct that is normally formed. And another important thing is like, of course, its setting time is 8 to 12 first. Since there is lead dioxide, it is having a messy nature. It stains the clothes. It have unpleasant odors and color. Very important thing, it is hydrophobic in nature. These are things that you have to keep in mind. It is hydrophobic in nature, and very important thing, it is very flexible so that it can be easily taken out of the mouth. But even though it have a very good property, because of the bad odor, we cannot place it in our mouth, right? And it is the only impression material that can be electroplated. Means electrolysis or metal electroplating can be actually done with the help of polysulfide. Hope you understand. Other names of polysulfide, it consists of lead dioxide, and final product, there is water as a byproduct. Because of these lead dioxide, it is having odor, color, discoloration, etc. But it is flexible. It can be easily taken out of our mouth, right? That was about polysulfide. This is condensation silicon. As the name suggests, there is again a byproduct that is formed, ethyl alcohol. So in the early case, there was water. Here it is ethyl alcohol. Again, all the disadvantage that was with polysulfide, here it become a advantage. First is like the color. Color was of course pleasant color and there was no stain. Of course, it is having a good odor. And one thing is less permanent deformation than polysulfide. That is another important property. Low tear strength. Tear strength means when we actually take the material out of our mouth, it should not tear. That was good for polysulfide, but here it is less, slightly less when compared to that of polysulfide. Next is hydrophobic in nature. Again, polysulfide, condensation, both were hydrophobic. Okay. Next is adhesion silicon. Adhesion silicon, as the name suggests, something is being added continuously. So there is actually no volatile byproducts formed. First is water, second is ethyl alcohol, third, there is no water or byproducts that is formed. And this is having, because of no byproducts, it have low shrinkage and lowest permanent deformation with best dimensional stability. Very important, three important points: no shrinkage, best permanent, no permanent deformation with dimensional stability. That is mainly because there is no byproducts that is being formed. Again, it is hydrophobic. The last is polyether. The polyether, you need to think it is hydrophilic. All the other three important materials were hydrophobic. Here it is hydrophilic. This is the first elastomer which was actually used for as an impression material, but the others, like, it had other functions, but it was derived to be used as a impression material. So that is one of the main important difference. Another is hydrophilic when compared to the other, and the tear strength is next to that of polysulfide. It is having good high tear strength when compared to that of actually polysulfide. Dimensionally, they are more stable, stiffest of all elastomeric impression material. So because of that, it is really difficult to take it out of our mouth. So these are the certain important differences that you have to place in your mind when you study about the elastomeric material. So agar alginate were hydrocolloids. Agar is a reversible hydrocolloid. The other is an irreversible hydrocolloid. And you need to think about the composition, mnemonics which I have taught, the reaction that is taking place, what is the byproduct, what is the problem with the byproduct. When we talk about these four elastomers, which is hydrophobic, which is hydrophilic, which have high tear strength, and second is like what are the byproducts which is formed and which has to be poured as soon as which we take place, which is having dimensional stability. All these important points has to be kept in mind. So hope like this was a class. It is not like a normal lecture class where we'll be explaining completely. But in here, I've just gone through the important points that have been continuously been asked for your NEET MDS examination, and just concised it completely. I hope I've covered most important things, and I have not covered color in this because I'll be actually completing that in the miscellaneous slide, right? So do repeat, see this, because in a single stretch, it is really difficult to understand this PPT because it is the physical property, and of course, it is a boring subject too. Keep on repeating, hearing this. And if any doubt, you can actually contact with the Idento side. Thank you and good night.